Hello viewers, today we are going to start a unit gaseous state. As you know, there are three states of matter: solid, liquid and gas. A substance can exist in any three states of these. It depends on their temperature and pressure. So, we will just start the introduction of gaseous phase, the gas laws and the ideal gas equation. Gas is a third state of matter where intermolecular forces are few and far between. It means that molecules are free to move around, rotating, vibrating and translate themselves through space. A gas has no definite volume or shape. It means a gas will fill whatever volume is available to it. Gases fill containers uniformly and completely. Gases can be compressed by the application of external pressure. It means we can liquefy gases, and at high pressure and low temperature they can convert into liquid state. Gases diffuse and mix rapidly and mix with each other to form mixture of any composition. They can exert pressure on the walls of the container in which these are enclosed. There are some uses of gases, like in metal industry, in semiconductor industry we use gases, in manufacturing industry, in glass industry, in chemical industry, labs, biogas industry, textile industry and many industries, as you can see in this slide. It means gases, those have lower densities, expensivity, diffusibility and compressibility. These are the major characteristics of gaseous phase. The properties of gases can be fully described in terms of four parameters. These are measurable properties. These are pressure, volume, temperature and amount of gas. As you can see in this slide, these parameters are pressure, volume, number of moles and temperature. These parameters are interrelated. If we have information of two parameters, we can easily describe the properties of two parameters here, because these are interrelated. Now start the gaseous laws. The gaseous laws is the empirical generalization based on experimental results. These gave rise to well known gas laws. Like all these laws are derived from experimental results only. First one was Boyle's law. Charles' law we will discuss is, then Avogadro's law, then we will discuss Dalton's law of partial pressure and Graham's law of diffusion. So, let us start with Boyle's law here. R. Boyle proposed a relation between pressure and volume. It states that the volume of a given mass of a gas is inversely proportional to pressure if the temperature remain constant. In other words, we can say that the pressure of a gas, as it increases, as the volume of the gas decreases at constant temperature. You can see in this slide as the temperature and number of moles are constant here. In these conditions, pressure is inversely proportional to volume. mathematically we can represent as volume is inversely proportional to pressure. So, that is V is inversely proportional to P. Now, we can write it here as PV is equal constant. If two gases are present, gas 1 and 2, for this the Boyle's law is P1 V1 is equal P2 V2. In this graph, it is easily visible that as the pressure is decreasing, volume is increasing here. In this graph, you can easily see this presentation. Let us discuss some examples of Boyle's law. A very good example of Boyle's law is a bicycle pump. As the volume of the air trapped in the pump is reduced, its pressure goes up and air is forced into the tube properly. Another example of Boyle's law is deep sea fish die when brought to the surface. As the pressure decreases at the surface, as the fishes are brought to the surface, the pressure is low, so the volume of the gas in their bodies increases. So, what happens in this case? It pops bladder, cells and finally fishes die. Let us discuss the Charles law. Jacques Charles proposed a relation between volume and temperature of a gas at constant pressure. In other words, we can say that the volume of a given mass of a gas is constant pressure is directly proportional to absolute temperature. So, mathematically we will write it as V is directly proportional to T. So, we will write it V by T is equal constant. If we have two gases 1 and 2, in that case it will be V1 by T1 is equal V2 by T2. In this slide, you can see it as the pressure and the number of moles is constant, in that case V is directly proportional to temperature. In this graph, as you can see here, as the volume is increasing, the pressure at constant pressure, the temperature is also increasing because it is directly proportional to volume. A very good example of Charles' law is thermometer. In thermometer, as the temperature goes up, the volume of mercury goes up too. As we have fever, our body temperature is high, in that case the volume of mercury goes up in thermometer. Another example of Charles' law is a football. Football inflated inside, and when we take it outdoor on a winter day, what will you notice? You notice that it shrinks slightly. Why? Because the temperature is low. Next law is Avogadro's law. Avogadro proposed a relation between volume and number of moles. He states that equal volume of gases under the same temperature and pressure will contain the same number of molecules. So, mathematically we can write it V is directly proportional to number of moles, that is N. In this slide, we have taken two parameters constant, that is pressure and temperature here. In this condition, V is directly proportional to number of moles. Now, the example of Avogadro law is that if we take two balloons filled with helium and oxygen, the same number of molecules are present in both balloons, but the balloon filled with helium is lighter. Why it is? Because of the lower mass of helium. Now, let us discuss next the Dalton's law of partial pressure. John Dalton proposed a relation between a total pressure of mixture gas, that is, he states that the total pressure of a mixture of non-reacting gases is equally to the sum of the partial pressure of the individual gases. So, we can write it mathematically as P total is P1 plus P2 plus P dash. In a mixture of two gases, the total pressure is simply the pressure of each gas in the mixture added, as it is visible in this slide that P total is equal P1 plus P2. Next law is Graham's law of diffusion. Thomas Graham states that the rate of diffusion of a gas is inversely proportional to the square root of the density of gas at constant pressure. So, mathematically we can write it R is inversely proportional to density. If we have two gases 1 and 2, in that case R1 by R2 is equal root D2 by D1, or we can write it root M2 by M1. Now, let us discuss what is this diffusion here. Diffusion is the movement of a fluid from an area of higher concentration to an area of lower concentration. Diffusion is a result of the kinetic properties of particles of matter, and the particle will mix until they are evenly distributed. As you can see in this slide, see there are some gaseous molecules and this one is mixing with this phase. So, this rate of mixing is known as diffusion. Effusion. It is the movement of a gas through a pore or capillary into another gaseous region or into a vacuum. Like in this compartment, when gases mix with this phase, it will go through a pinhole. So, this is known as effusion here. Its very good example is gaseous exchange in our body. Carbon dioxide and oxygen in our blood, in our lungs, which saves our life. So, it is very good example of Graham's law of diffusion. So, after combining these three laws, Boyle's law, that is P is inversely proportional to volume, Charles' law, that is V is directly proportional to temperature, and Avogadro's law, that is V is directly proportional to N. So, after combining all these three laws, we get ideal gas equation, that is PV is equal nRT. In this equation, V is the volume, T is the temperature, N is the number of moles, P is the pressure, and R is the ideal gas constant. R has different values, it depends on the unit we use. So, these values can be expressed in different units, that is R is 0.0821 liter per atmosphere per mole. R is 8.314 into 10 to the power 7 ergs per Kelvin per mole. R is 8.314 joules per Kelvin per mole. R is 1.987 calories per Kelvin per mole. So, these are the different values of R with different units here. So, what we have discussed here in this lecture, the characteristics of gaseous phase. As I told you before, gaseous phase has expansivity, diffusibility, compressibility. These are the proper and main characteristic of gaseous phase. Then we discussed gas laws like Boyle's law. In this case, pressure is inversely proportional to volume. So, what did we write here? PV is equal constant. In Charles' law, volume is directly proportional to absolute temperature. Mathematically, we wrote it V by T is constant. In Avogadro's law, V is directly proportional to number of moles. So, V by N is constant here. Then for Dalton's law of partial pressure, the P total is equal partial pressure of gases, that is P1 plus P2. Then Graham's law of diffusion, that is rate of diffusion is inversely proportional to the square root of density, and then we discussed their application in daily life. After that, we discussed the ideal gas equation and the different numerical values of ideal gas constant. In next session, we are going to discuss the assumptions of kinetic gas theory and then we are going to derive it. Thank you.